I'm ready to continue learning reactions of alkenes and alkynes. How about you? Let's do it. I have an alkene reacting with HBr. HBr is an acid, so this is an alkene reacting with an acid. Alkene is the nucleophile. Nucleophile attacks the electrophile. The H is the electrophile because it's got a partial positive because bromine is more electronegative and pulling electrons away. Hydrogen can only make one bond at a time, so you gotta make a new one, break an old one. Hopefully you've been studying some carbocation stability stuff, and you know that the H should go here because that means the carbocation should go there. And then Br is the nucleophile, the carbocation is the electrophile, and you attack. Bromide attacks the carbocation, and you get your product. But then I ask the question, would you expect the product as obtained in this reaction to be optically active or not? Wait, what? Stereochemistry rears its ugly head once again. You said, I thought that was last week. I thought we could forget stereochemistry now, and I say, hold up, you can't forget stereochemistry. Organic is too cumulative for that. So the question is, right here where that bromide attacked, that is a new asymmetric carbon. And so when you make a new asymmetric carbon, like this one, you need to understand and know the mechanism that you went through in order to determine the stereochemistry of that product. So if I back up one step, I have a carbocation that is sp2, and all things that are sp2 are trigonal planar, and something that is planar, it means it's flat. Okay, so when that bromide comes to attack, it could attack from, we'll say, the top side. And if bromide attacks from the top side, it means bromine would end up joining like that, and maybe it would push the methyl backwards. You could also think of it as pushing the ethyl backwards or pushing the propyl backwards. It kind of depends on where you put your bromide as to what you push backwards. The gist is, we make a new tetrahedral carbon, and bromine's going to approach from one side to make this, but bromide could have also approached from the other side, as in the back side. It's a trigonal planar thing, the top or the bottom, and push the methyl the other direction. Again, you could have dashed and wedged different things there than I did, but I often do it like this. Let me explain. So if I did some R's and S's of these guys, is this R? Is this S? It's R. So this is the R stereoisomer. This is the other one, is the S stereoisomer. Okay, so because this reaction went through a carbocation that is sp2 and trigonal planar, when the nucleophile attacked said carbocation, it generated these two products. Because the carbocation is trigonal planar, do you think this is important? Yeah. Because the carbocation is trigonal planar, when the nucleophile attacks, it can attack from the top side or the bottom side. It will attack from both. So we would say that we get a 50-50 mixture of these two compounds. These two compounds are enantiomers, and a 50-50 mixture of enantiomers is called a racemic mixture. That's illegible, I know. That's a racemic mixture, so we make a racemic mixture. Racemic mixtures are not optically active. Wait, what? I thought enantiomers are. It's true, enantiomers are optically active. If I had only R, I would have an optically active product. If I had only S, I would have an optically active product. But a 50-50 mixture of the two is optically inactive. It's like a tug of war. This guy wants to pull the light one direction. This guy wants to pull the light the other direction, and nobody wins. So you would get an optical rotation of 0 in a reaction like this. You think you got it? Let's try another one. This is acid and water added to an alkene, so similar to the last one, but a little different. I think we probably should go ahead and walk through the mechanism because you've only seen the acid and water one once, but you've practiced it way more than that, haven't you? I hope. I'm going to make a carbocation. This one's secondary, either side, it doesn't matter. Water attacks that carbocation. This one's a different kind. Remember, water has a hydrogen connected to him. He has 2 hydrogens connected to him, and he brings both along for the ride. And then water will come clean everything up. Like so. To give me my final product. So then you have to be ready to answer the question, do you expect the reaction, the product, as obtained in this reaction, to be optically active? The first question you ask yourself is, the carbon that got attacked, the carbon that was the carbocation, is it now asymmetric? Yep. Because that carbon is asymmetric, you need to look back through the mechanism, and the mechanism went through a carbocation that's trigonal planar, which means when water attacked, he will attack from the top and the bottom. He will attack from both sides. So I could draw my product, I should draw my product as the wedge OH and the dash OH. Could I represent my molecules a little bit different way and it still be legit? Yeah, but I think one of the easiest ways to try and ensure that you have the best chance at getting stereochemistry right is to dash or wedge the thing that attacked the carbocation. Occasionally that's not quite the case, but as we get more practice, we'll get better. This next one, let's not draw a mechanism. Let's draw a product. CH2, I don't love that I chose to draw this in a Fisher projection, but it is what it is. The OH is going to get connected to that carbon because the H is going to get connected to that carbon. So is that new carbon that you're going to create here, that new tetrahedral carbon, is that going to be asymmetric after water attacks? Yes. Because it's going to be asymmetric after water attacks, you would end up with an OH on one side and the OH on the other side. But wait, what's so different about this one? This one started with an asymmetric carbon down here. Remember, D is deuterium. That's heavy hydrogen. It's hydrogen that has a neutron instead of just being a proton. That's deuterium. So this is an asymmetric carbon already, and it's still an asymmetric carbon over here after I add the new groups. But the reaction did not happen at that stereocenter, so that stereocenter stays the same. Okay, what do you want me to know about it? These two products in the last reaction are what relationship to each other? They are diastereomers. Because one stereocenter stayed the same and one stereocenter is different. One stereocenter is the same and one stereocenter is different. They are diastereomers. Why did you make diastereomers in the bottom example and you made enantiomers in the previous two examples? Well, that's because my molecule in the bottom purple example already had an asymmetric carbon. So don't start memorizing when I make a carbocation, I always make enantiomers. That's not necessarily the case. When you do a mechanism that goes through a carbocation, that carbocation is trigonal planar and you will always attack from the top and the bottom. Sometimes that generates enantiomers, sometimes that generates diastereomers, sometimes it only generates one product because you don't have any asymmetric carbons. So don't start memorizing this or that or that. Don't do that. Okay, one little note down here. When you make enantiomers are always formed in equal amounts. That's almost illegible back there. They're always formed in equal amounts. Diastereomers may not be. Sometimes there are other steric factors going on, like things like this influence the electronics of the neighboring substituents. So diastereomers may or may not be created equal. We will discuss more examples of this later. For now, I just want you to know enantiomers are always created equal, and that's going to make a racemic mixture when you have equal enantiomers. Diastereomers may or may not be equal. Okay. If we were in a classroom environment together, I would say, these are your turn. Get started. Good luck. But I suppose we should do them together, / I should do them for you. Here's how the mechanism goes. Make the secondary carbocation. Chloride attacks that carbocation. Why am I drawing that chlorine still wedged? Because did the reaction happen at that carbon that has the chlorine wedged? No, leave it alone. In this new carbon, in this new tetrahedral carbon where my chloride attacked, is that an asymmetric carbon? This one? Yep. So if I said draw all products including stereoisomers, you would draw these two products. But there are two asymmetric carbons. Aren't there 4 possible stereoisomers? Yeah, there are 4 possible stereoisomers, but this stereoisomer never forms in this reaction whatsoever. Not happening. This stereoisomer, this stereoisomer is identical to that one. Why are those identical? Because this is a meso compound. Yep. So this is a meso, therefore that molecule on its own is optically inactive. This molecule is optically active because an enantiomer does exist, but the enantiomer is not present to cancel this out and call it a racemic mixture. So these orange guys are diastereomers of each other. So if I ask the question, would you expect the product as obtained in this reaction to be optically active, you would say yes. Wait, huh? So when I say the product as obtained, what that means is any sort of mixture of products that you get, that solution, that sludge, that set of products, would, if you took that mixture and stuck it through a polarimeter, would you get an optical rotation? The answer is yes for this one, because this one does not affect the light at all. This one does affect the light. So the mixture still provides an optical rotation because those two do not cancel each other out. It's not a racemic mixture. Whew, I think I might have that. That was so fun. How about some more? HCl. Make the secondary carbocation. Leave the chlorine wedged, because that's how he started, and we ain't bothering him. I get this. Does this have a new asymmetric carbon where that chloride attacked? Yeah. So I really should get those 3 little equals means that's equivalent to / I often use it as saying I'm drawing the same thing but providing more detail in the next version. So I get those 2 green guys. Would you expect the product as obtained in this reaction to be optically active? Yes. We're going to put some... What should we put? We will put some letters so that you can answer some questions and do some explanations on those for me. That would be grand. I'm feeling good. I think I'm getting this acid addition to alkenes thing. Let's do this. Off to the races. Make the secondary carbocation. Chloride attacks with his lone pairs. And we get this. And you say, yeah, of course, that's an asymmetric carbon. So really, I actually get this. These. Oh, that's real crooked. I'll straighten it out in a moment. I really get that racemic mixture, that pair of enantiomers. Yes, yes, I do. And these are enantiomers. But, check this out. That product is created, it was green in our last slide, at 17%. The other 83% of the product is this. Wait, what? How the heck did that happen? I just thought I was understanding this. Ugh! Organic. Oh my god. Yeah. So the way this bottom product happens is through a carbocation rearrangement. We'll draw it. Give me a second. But this bottom product happens through a carbocation rearrangement. What's the relationship between these two molecules? These two molecules are constitutional isomers. Constitutional isomers, for what we know so far, constitutional isomers will only be created if you have a carbocation rearrangement. Stereoisomers are created from a single carbocation, but constitutional isomers, nah, that's a rearrangement kind of thing. Okay. So if we put our stereochemistry thoughts aside for a moment, and we go back to the carbocation that was formed in this reaction. That carbocation is a secondary carbocation. Secondary is not as stable as tertiary. So a carbocation shift can happen. What kind of shift happens? Well, a lot of shift happens. The way this shift happens is a methyl that's sitting on the carbon next door to the carbocation hops next door. Note that curved arrow is coming from the electrons that are holding on that CH3. That CH3 hops next door and carries, and so it's the carbon and his two electrons, and all three hydrogens hop next door. Let's see if we can keep that color coded. There's the green stuff. And then my purple CH3, there's nothing special about the CH3. I'm just showing him explicitly to help you follow him a little bit better. My purple CH3 hopped next door like that. Why would that happen? Because where that purple CH3 left, the spot that it vacated, is now a carbocation. What kind of carbocation is that? It's a tertiary carbocation. Tertiary is more stable than secondary. This thing, this wacky thing we just did, is called a methide shift. It's called an ide because it's the methyl migrating with its electrons. I have bad habits, and I often will call it a simple methyl shift, but it's officially a methide shift. Methyl shift, methide shift, it's the same thing. The reason it's often called ide is because it's moving with its electrons, and students need to keep track of those electrons. Okay. After I do that methyl shift, methide shift, then my chloride attacks that carbocation, and that's how I get that other product that was shown on the previous slide. This one. This thing, if we went back to revisiting our stereochemistry discussion, is the carbon that got the chloride now asymmetric? Nah. Is the carbon that underwent the methyl shift, methide shift, asymmetric? Nah. So this blue molecule is the only molecule that's created from this shift. There's no stereoisomers of the blue molecule because there's no asymmetric carbons in the blue molecule. You see how it all gets cumulative pretty quickly? I think I got this acid addition stuff, though. And then you tell me, wait, methyl shift, methide shift's not the only kind of shift. It's true. Carbocations can rearrange somewhat frequently. There are three types of rearrangements, three main types of rearrangements. There's a methyl shift, a methide shift, a hydride shift. Any idea why it might be called hydride? That's a hydrogen with its electrons. And we'll say a ring shift. You create a new carbocation if the new carbocation is more stable than the one from which it came, like secondary will migrate to become tertiary if at all possible. Or if it's of equal stability. We're not trying to get in a rabbit hole here of shifting and shifting and shifting some more, so we'll explain some more details about this one. Don't just say this shifts around and around and around. No. Okay. HBR. I think I can draw these arrows. Hopefully you're feeling a little bit bored at this point with all these arrows being the same. Yeah, did you ever imagine that? I hope you're feeling a little bit bored. That's the way those arrows go, yes. Do I create a new asymmetric carbon? Yes, but we'll talk about stereochemistry in a moment, because the real point of this discussion is not stereochemistry stuff. It's carbocation rearrangements. So I analyze the carbocation that I made, and I see that it's secondary. There's a possibility to become more stable than secondary, as in tertiary is more stable than secondary. Is there any way that you could shift this thing to become tertiary? A lot of students want to say, sure, hop that methyl next door. And I say, nah, if you hopped that methyl next door, you would have a carbocation left here, and that would be a secondary carbocation after the methyl left. That would still be secondary. That ain't no good. What I can do is shift the hydrogen next door. There was a hydrogen lurking in the background the whole time right there, right? Yeah. So that hydride hops next door. It is not required to draw that out explicitly, but I did it anyway just to make sure you're keeping track of where it went. When the hydrogen goes over there, this carbon is going to end up with the plus charge, plus tertiary carbocation. Whoop, whoop, whoop. Bromide attacks. Ta-da! I attacked from down at the bottom, so I'll point my bromine down there, but we'll discuss all the specifics of all that later. Is the carbon where the bromide attacked asymmetric? Nope. So, we get the blue product and the purple product, and the relationship between the blue product and the purple product is that they are constitutional isomers. Blue and purple are constitutional isomers. The blue should also create two stereoisomers. This one and that one. And those two green things are enantiomers. The one on the left is the S configuration. The one on the right is the R configuration. So this reaction really creates three products. These three products. Would you expect the reaction as obtained in this reaction to be optically active? No. Because these are a 50-50 racemic mixture, they would cancel each other out. They would have a tug of war. One wants to go this way, one goes that way. Nobody wins. And this one is achiral because it has no asymmetric carbon. So nobody wins. There is no rotation of light if you had this mixture and put it in a polarimeter. We cool. Kind of, sort of. Okay. I may as well show you the actual percentages of the breakdown, because I forgot to mention that you have to get good at labeling the major isomer. This, because I can look at the numbers, I know is the major isomer. The major constitutional isomer will come from the most stable carbocation. The major constitutional isomer will come from the most stable carbocation. All right. I really think you should try this on your own. I think I got enough gas in the tank for another. How about you? Alkene attacks the acid. Alkene is the nucleophile. It attacks the acid because acids are electrophiles. Make the secondary carbocation as opposed to the primary carbocation. Nucleophile attacks. The nucleophile this time is water. Water attacks. He brings along both hydrogens he was connected to. Water cleans up the mess. And here we have the product. This product does have an asymmetric carbon, so we will concern ourselves with stereochemistry, but before we go do that, tell me, do you think this carbocation can rearrange in any ways that we have already discussed? Yeah, it can. So I start another line of my mechanism. You knew this was a mechanism, right? Maybe I haven't called it that many times. I'm struggling over here. My cat is attacking me from under the table, attacking my arm, and I cannot get my mechanism drawn. Let's do a hydride shift. Youch. I hope you found that amusing. My cat certainly did, but I did not. A hydride shift where the hydrogen moves over here, and there's a positive charge there. Water attacks. We're going to get a little crowded over here. Then water cleans up. Ta-da! Here's my product. That got a little straight, but that's supposed to be a kink in there. Yeah. Guess what? There's a third type, a third constitutional isomer here. A second way that carbocation can rearrange. Can't do a methyl shift. There ain't no methyl to shift. We've already done a hydride shift. So I guess that means a ring thing. It does mean a ring thing. Let's do that ring thing. I'm going to highlight this bond in orange, but I'm also going to number my carbons. So in order to do a ring shift, I need to unplug one of the carbon-carbon bonds that's holding my ring closed. So I could unplug carbon 3 and 4 or 3 and 7. I've chosen to do 3 and 7, but it's a symmetric molecule. You're going to get the same thing regardless here. But I've numbered those carbons for a reason. I'm going to try to keep things in the same general format. Oops, that got wiggly. In the same general format so that I can highlight this is the bond that shifted. And here are my numbered carbons. So, okay. Which bond did I unplug? I unplugged 3 and 7 and made a bond from 7 to 2. Who lost in that transaction? Carbon 3. So who's my positively charged carbon? Carbon 3 is my positively charged carbon. Then water attacks carbon 3. If you haven't noticed already, this is just a standard 6-membered ring at this point, with a methyl on one carbon, and now a water has attacked on the neighboring carbon, and then a water cleans up the mess, and you're left with this. Those 3 products, purple, blue, and green, are your 3 constitutional isomers that this reaction forms. Are you ready to talk stereochemistry of these guys? Sure you are. So we've already said the blue one up there has an asymmetric carbon. Does the green one have any asymmetric carbons? Nope. Does the purple one have any asymmetric carbons? Yes. The purple one has 2 asymmetric carbons. All right, let's start with blue because that's where we started, as well as that one's easier because there's only 1 asymmetric carbon. 1 asymmetric carbon, that asymmetric carbon used to be the carbocation. Therefore, when that water attacked, it attacked from the top, it attacked from the bottom, it attacked from both. It made a racemic mixture of blue products. Okay? The green is the only product made because no stereoisomers of that guy exist. That's the only thing. And then the purple, I wish I had not had to clean off my board to save myself some space. The purple has 2 asymmetric carbons. So if I drew all stereoisomers, all 4 stereoisomers of the purple, should this reaction create all 4 isomers? Yes, it actually should. And that's where I wish I hadn't had to erase the whole mechanism. If I went back and put numbers on here that correspond to the way I had things numbered previously, remember carbon 2 and 7 are what made the new bond? Yeah. So carbon 3 is asymmetric. Is there anywhere in your mechanism where carbon 3 was a carbocation? Yes. So because carbon 3 used to be a carbocation, that means carbon 3 gets racemized. Okay? Is there anywhere in your mechanism that carbon 2 was a carbocation? Yes, carbon 2 is actually that carbon right there, that carbon that was the original carbocation. So carbon 2 used to be a carbocation, carbon 2 should also be racemized. So because both of those should be racemized, both of those asymmetric carbons should be racemized, we get a racemic mixture of all 4 possible stereoisomers. I said racemic mixture, but I should clarify. These 2 compounds are enantiomers, and those 2 compounds are enantiomers. I get 2 pairs of enantiomers out of this. That was a big example. Did you follow along? Okay. So all of the mechanisms that we've done were acid additions to alkenes so far. What about acid additions to alkynes? This is one example where we won't talk a lot of detail about alkynes, but because alkenes and alkynes are in the same functional group family, I expect you to make a lot of assumptions, generalizations. I expect you to already know how this first mechanism goes without me even having to show you. Problems like that are what you should expect on our tests on this stuff. I may ask you a specific mechanism that we've actually covered, but more than likely I will ask you to use your foundational knowledge to draw a mechanism that is something we have not covered exactly. So, are you ready for that? I'll draw this first 1, maybe 2 together, but you really should probably test yourself and see if you could do these on your own. One difference in alkenes and alkynes. Alkenes have 1 pi bond, alkynes have 2. So you need to specify the number of equivalents you have sometimes. That EQ means equivalence. What that means is I'm adding 1 mole of HBr for every 1 mole of alkyne that I've got in solution. So, pi bond attacks, like so. I make the secondary carbocation because that's more stable than primary, and bromide attacks, like so. Done. Because I only added 1 equivalent of HBr, I only added 1 H and 1 Br. What if I had two equivalents of HBr. Pi bond attacks, makes a carbocation. I'm going to not show the carbocation. Carbocation gets attacked by Br. I end up making almost the exact same product I have up above. The only difference is I've got a methyl and a hydrogen on one side instead of two hydrogens. Note, I have drawn this like a Z isomer, highest priority. I've drawn it like Z, but really it would make both E and Z products. You follow me? Yeah. But I'm adding two equivalents of HBr. So from here, it's a normal alkene addition. And my alkene should put the next H on the right carbon to make this carbocation. And occasionally, students that are really on top of their game say, but there's a bromide connected. That carbocation's not super stable. And I say, oh, contraire. That carbocation is extra stable because that carbocation has resonance. Oh, mind blown. That carbocation has resonance, so that carbocation is extra stable. So bromide attacks that carbocation, and we get our final product, which I'm tired of drawing C's and H's for, but I've committed to it now. Our final product is this. Two Brs added to the same carbon, two H's added to the same carbon. Yeah? It's an alkyne. I do actually think the last one is important enough to talk about, but I've been debating whether I wanted to go over the mechanism with you guys or not right now, and I think I do not. But I would expect you to predict the product of something like this. There's acid, there's water, there's pi bonds. Okay? I know I would expect you to predict something like this to happen after one of those pi bonds reacts. You would do that, right? Yeah. This compound is special. This compound has an alkene and an alcohol on the very same carbon. It has an alkene. That's real illegible. Let's try again. It has an alkene and an alcohol on the very same carbon. That's called an enol. And enols are not very stable as enols. They do this fancy process called tautomerization. Yeah. That enol tautomerizes to become a ketone. What? Yeah. Hold on. Enols tautomerize to make ketones. Where there's one carbon involved in the alkene and the alcohol functional groups. That's a special enol. It's an equilibrium process, this enol stuff, but equilibrium favors the ketone variety much more than the enol variety. It favors the carbonyl variety much more than the enol variety. A couple of things, a couple of details about this. This is called a terminal alkyne. A terminal alkyne is kind of difficult to get to do this reaction unless you add mercury to the mixture. So we pretended like we could think about this process having not included mercury because we don't know what mercury does yet. Coming soon to a theater near you. But so far we don't know what mercury does in this reaction. But the truth is mercury is actually needed to get this product, which then gets that product. If mercury is not there, this product is not actually obtained when you have a terminal alkyne like that. Details, I know. So because the mercury is actually involved, this reaction does not officially go through a carbocation. because the mercury prevents it going through a carbocation. So you don't have to know the mechanism just yet, but no carbocation, therefore, that's what those three little dots are if you didn't know that. No carbocation, therefore, no rearranged products are possible. That's kind of nice, just when we went through all that rearrangement mess. Yeah. If you don't go through a carbocation, that carbocation can't shift. Duh. That's nice. So that's acid additions to alkenes and alkynes, and that's all we're going to do on acid additions.